I again have a great pleasure of announcing someone. In this case, Sam Scimemi, to me, Mr. ISS, Mr. International Space Station. And I bet he's not that just for me. Sam has nearly 3 decades of experience in human spaceflight, which translates in Space Shuttle, of course, in working with the ISS, obviously. He worked at JSC, Ames, Goddard, and here at NASA headquarters. They're going to talk about Mars analogs, and I'm always interested in that because I have been involved with Mars analogs for many years here on Earth. And it gladdens my heart that the ISS will be used to practice for Mars next year. Well, without further ado, Sam Scimemi.
All right, thank you, Art. I put up Chris to make an announcement yesterday, and then I got hauled off outside the building. The announcement I was going to make yesterday was that station was passing over DC on a very clear night at 8:42 last night. I don't know how many people had a chance to see it last night, but that was the last pass over DC for this time. Also, a couple other announcements I'd like to make. On May 1st, AAS will be hosting an event at the Russell Senate building that will highlight the research being conducted on space station. And Charlie Bolin will be there, Gerst will be there, and a panel across commercial, NASA, researchers and technology developers will be there as well. And on April 29th at NASA headquarters, we'll have an exploration forum there to sort of recap and give a more in-depth with all the players of NASA, of exploration and ISS and everything that we're doing to get us to Mars. So with that, I'd like to introduce our panelists. First panelist is Dr. Bill Paloski. He's the manager of the Human Research Program at JSC. He completed his PhD in biomedical engineering at Rensselaer Polytechnic.
RPI.
Yeah, RPI. Yeah, that's it. In 1982, and he spent 3 years as an assistant professor there in biomedical and mechanical engineering at Boston University. Since joining NASA, he has held several numerous and management positions. He's also been a professor at Human Health and Performance at the University of Houston. Next, we have David Korth, who I've known for quite a long time, back in the Eagle Building days, down at JSC. He is a flight director for Space Station at the Johnson Space Center and has been for the past 7 years. He has worked on the Space Shuttle and Space Station programs, and I believe all in MOD. Is that correct, Dave?
Yep.
For several years. He has a BS in Aerospace Engineering from Texas A&M, and he's performed some graduate work in electrical engineering at the University of Houston. Next, we have Dr. Terry Fong from the Ames Research Center. He is the director of the Intelligent Robotics Group and is the project manager of NASA Human Exploration Telerobotics project, and has tested advanced telerobotics systems on the International Space Station with the crew, and he's going to talk about that. He received his BS and Master's in Aeronautics and Astronautics from MIT, and has a PhD in Robotics from CMU, but I don't know where that is. With that, I'll start with my presentation, then we'll just go down with the rest and then take questions at the end. So I'm gonna stand up and do this. The title of today's panel is Practicing for Mars, and I'll give you a little bit of highlight of practicing on the way to Mars, and what it's like, what it's really not like. So first of all, this is not the road to Mars. It is not going to be all flowers. It's not going to be all pretty and lined up like that. This is neither the road to Mars. Here, if you know the story, everybody gets what they want in the end. Well, we have to be careful what we want. If we want to go to Mars, let's go to Mars. If you want to go to Mars a particular way, well, you may not get that particular way. But if the goal is getting to Mars and eventually getting to the surface, if that's our goal, which I think it is our goal, how we actually do that is a matter of how much money we have and what are our technical and human health risks and things of that nature. This should look familiar to most of the engineers in the room. This is how we get to Mars, through a bunch of circles and arrows and graphs and hopefully someday a critical path. So this is what we as a community needs to come to consensus on, how we go from here in space station to Mars. Now, we've seen this several times now. Now, this is not a roadmap. It's sort of the context of the stages of getting to Mars, and I won't go through this again. But again, we're back here in Earth Reliant, just to remind everybody where we're at, and doing the research and technology development and the Mars simulations here on station in a close proximity to the Earth. You've seen this also before, yesterday for me, in a different format. I just want to emphasize again how we are tied to the Earth in communications, crew exchanges, logistics, crew and atmospheric samples that come back, our modified hardware that we bring back up, emergency crew return, and we have a convenient way to get rid of trash. So the simulations that we do on station is all conditioned by these things. And we're trying to learn how to break these connections to the Earth in our simulations, in our research, in our technology development. So we want to go from this to this, where the only link you have is a comm link, and actually a very long delayed comm link. So to recap again what we're doing on station, and as a fundamental proving ground for our first steps beyond low Earth orbit, the two major things we have going on is our life support system and the upgrades to that to be able to build the next Mars life support system, and our crew health research and crew performance systems development, and all our other crew support activities and vehicle activities like rendezvous and docking. And last but not least, our Mars simulations, which is the focus of today's panel. And all these things need to lead to something. We talked about this yesterday and throughout the whole conferences. All the things we're doing in research, technology development, simulation has to lead to the next step. And all the things we need to do in our next steps is to break the logistics chains, reduce the day-to-day reliance on the ground, extend the time and distance from the Earth, using the high reliable, low maintenance life support systems, confirm our crew health and performance in our long duration missions beyond LEO, and validate and practice our long duration crew performance. If you put all those things together and breaking the links to the Earth, to do this before we go to Mars is, in my opinion, necessary in a mode of a shakedown cruise before we go to Mars in the cislunar space area, to put all these things together to show that we can actually keep humans alive, keep them productive, perform science while we're still there in cislunar space. And I'd just like to leave you with one thought before I get off the stage. There are no flowers on the road to Mars. With that, Dr. Paloski.
I'll try standing as well. Oops. Let's go back to that first one. Okay. So my day job is to run NASA's Human Research Program, and this program is focused on trying to reduce the risk that crew members might be exposed to during any exploration missions. And the worst case, as you might expect, is a mission to Mars, 30 months away with long communication delays, and in a very small cabin cooped up with 4 of your best office mates for all that time. We have about $160 million a year to invest in research. We have about 200 researchers from around the nation that we sponsor who are working in our program, and we work extensively with our Russian partners and other ISS partners as well as non-ISS partners to try and leverage their knowledge and their scientific expertise, and in some cases their resources. In order to understand the human issues, and by the way, we get this funding from Mr. Gerstenmaier in part because we see now the human system as possibly being one of the major impediments to being able to take one of these long duration missions. I think we can build the systems to do that, but it's hard to get the people there and back. So we look at the risks that people are exposed to based on the hazards, and the hazards include artificial or altered gravity fields, and this includes the microgravity exposure during transit, hypogravity on the surface, G transitions between Earth gravity and zero gravity and Mars gravity and back. And we also lump in launch and landing loads associated with those transitions. Second major hazard is isolation and confinement, and we lump in with that altered light dark cycles. And these things, of course, have an important effect on behavior and performance. Third is the hostile closed environment. And this has two sort of flavors to it. One is what kind of stuff is in that environment? What's the atmosphere that's required to support life? What happens to microbes? What sort of dust might you be exposed to on the surface, and what toxic effects might that have? But second grouping in there is how do you lay this out? How much volume does a person need? What's the configuration of that volume? What do the displays and controls need to look like, and so on, the human factors parts of it. The fourth major issue, and it is a very significant issue for Mars missions, is increased radiation. And while we might be able to use ISS for simulating many aspects of a deep space mission, we can't use it to simulate the radiation environment, because the Van Allen belts protect us from a lot of the galactic cosmic rays that have devastating effects on humans. And then finally is distance from Earth, and that has an effect not only on behavior and performance, but also on our ability to return crews quickly. So if there's a medical event, we have to take everything with us that's required to take care of that event instead of evacuating back to Earth as we head out on a Mars mission. We use a number of analogs to try and answer the questions that we have to answer. As you might guess, there are not enough subjects, that is crew members, available in the lifetime of the space station to get all the answers to all the questions. So where possible, we use analog environments, and analogs are used to simulate part or all of the deep space experience. So we use, the primary analog we have, of course, is the space station, but we also use a radiation facility at Brookhaven National Laboratory to produce high energy, high mass particles that we can then expose animals, rodents, and tissues to look at the biological effects. It's not ethical for us to expose people to these kinds of radiation environments, so we have to use other species. And then we use a number of ground-based analogs. For many years, the primary analog had been bed rest, which simulates some aspects of the physiological deconditioning associated with zero G, or reduced gravity. And we use facilities at University of Texas Medical Branch for a very long time in concert with the NIH. And we recently have begun negotiations with the DLR Institute, who have opened up a fabulous new bed rest facility at their facility near Cologne. We use isolation facilities, and I'm going to focus a little bit more on isolation facilities the rest of this talk. But Antarctica and isolation chambers in Russia, and ones that we have here in the US, I'll talk about in some more detail. And then we use environmental chambers to look at gas composition and such things. The latest isolation chamber that we have, because behavioral health and performance is affected by so many of these hazards, the latest facility that we set up used to be the Habitat Demonstration Facility. It used to be out in the desert someplace and was used for training crew members. We've brought it into a building at JSC and refurbished it so that people can live aboard it for up to 60 days at a time, crews of 4. And with this facility, we can study behavioral health and performance. We can study communications delays and autonomy, human factors, and also some of the exploration medical capabilities that we're developing for autonomous medical care on long-duration missions. These kinds of facilities have different kinds of characteristics. The one that I just mentioned, the HERA, or Human Exploration Research Analog, is limited in two ways. One is that we can only do 60-day missions, and two is that it's not a hazardous environment. So some of the psychological issues, people know that are in the chamber that they can walk out whenever they want. We also are looking at using the Mars chamber at IBMP in Moscow, which reduces one of those problems. That is, we can do up to 500-day studies of crew members isolated in that chamber and look at their interactions together. And then we go to Antarctica for a higher fidelity simulation, but at Antarctica, we're superimposing our studies on working groups that are doing other activities, so it's a little bit harder to get control over what we do with them. We have a fairly robust program that we just negotiated with the Russians last week when we were there, to look at using our short-term analog for a number of missions in FY15 through 18, and to begin using some longer-term analogs in their facilities from 16 through 18. And this is all in preparation for a series of new one-year missions that we've proposed to the agency that would fly another 5 or 6 missions with 2 crew members each, 1 Russian and 1 US, for 12 months at a time, to be able to look at some of the behavioral health and performance aspects of longer duration missions, as well as physiological adaptation and some of the medical events that we might expect to occur. Other ground-based analogs that we use each have some strengths and some weaknesses, but they include things in the Antarctic, the Arctic, underground. There's a very nice caves facility in Sardinia that our astronaut crews have been going and training, doing team training in for 1 or 2 weeks at a time, and we're beginning to talk about how we might do research on the teams that go underground for that period of time. NEMO, which you may know about, which is an undersea analog off Key Largo in Florida. We're starting to think again about maybe having to use artificial gravity, at least in part, during one of these missions. And so there's a facility at Ames Research Center, a 52-foot centrifuge that we could have people live aboard for weeks at a time and look at the effects not only of isolation but also of rotation superimposed on that. NVHAB that I mentioned, and then we also use analog populations, people who are in high-pressure environments that might be similar to what the astronauts experience. So we've been doing things with the mission controllers, flight controllers. We're looking at submarine populations and also oil rig workers who are out in the Gulf or in the North Sea, isolated in hazardous environments for long periods of time. So overall, the path to Mars, from my perspective, is one of reducing risks, that is doing the research and technology development to mitigate the problems that the crew members are going to be associated with. ISS is a wonderful test bed for most things, but it just doesn't have the throughput that we require for all the science that we have to do, so we go to ground-based analogs like this along the way. And at that point, I'll stop and leave it to David.
Okay, thanks for having me here. Appreciate the opportunity to talk a little bit about station and operations. And as both Bill and Sam mentioned, there is a role for station in exploration. There's also a role for ground analogs. So station is not the end-all be-all of how you get to Mars. Let's see if I push the right button. Okay, first what I wanted to talk a little bit about is what is space station, what goes on in space station, because it'll kind of set the stage for why station's important, what are some of maybe the limitations of how you can use station as a test bed, and other things that we've learned by participating in the international effort that is space station, in addition to the tests that we are currently doing and plan to do on station. So what is it like to live on station? As you can see, we have a regimented work life that we set up for the astronauts on space station. And it also ends up being regimented for the ground teams on the ground in the internationally diverse control center team that we have. We put up people today on 6-month rotations. We call them expeditions. As you heard, starting next year, we're going to start periodically putting crews up there for 1-year rotations. Crews get holidays, they get days off, they have work time during the week. I kind of have a breakdown, and I added this up to make sure it adds up to 24. We don't break the boundaries of physics on station, so yeah, it is a 24-hour workday. And some of it may seem excessive. We talked a little bit yesterday in one of the biomedical panels about exercise and how much time do we devote to exercise. This is heritage information that we've learned from our experiences in Skylab shuttle, from working with the Russians and their experience on the Mir station, that you need a regimented exercise program with the right kinds of devices, resistive cardio, to keep the health and maintenance of the crew, because that's awfully important. The other part of it is, the other piece that needs to be discussed and Dr. Paloski talked a little bit about it, is the psychological support aspect. We have become really good at psychological support for space missions, and Station today represents the state of the art in psychological support. So if you go back and look at the Apollo and then the progression into Skylab and the Mir Station and even early station, you'll see a progression of how we provide psychological support for the astronauts. And that's in addition to psychological conferences, but it's keeping in touch with people on the ground. We have routine conferences that we perform with the crew. We made a conscious decision early on when we formed Station that the crew is going to be part of the planning process. We're going to keep them involved in knowing what's supposed to happen next week, what's going on today. They're the Johnny on the spot people. They have the situational awareness of the work environment. We have the objectives and the mission requirements. So the kind of symbiotic relationship that we have, they're part of the planning process. We keep up with the routine medical conferences, and then there's the as required conferences with management, things like that, to keep in touch and work through procedures. And then, of course, the psych support, which we have email. The crew has internet where they can surf the internet. We started years ago with what we call the internet phone, or the IP phone, where they can pick up a phone and call anybody on the Earth. Movies, books, recreational items, things like that. It's important to understand that for Station, we have evolved in our space culture. The astronauts have become used to it. We on the ground are used to this level of psych support. When you start talking about getting further away from Earth, going to Mars, as Sam's picture pointed out, where the only thing that ties you together is communications link, and that communications link could be delayed up to 20 some odd minutes one way. This becomes a huge aspect that we need to address. A lot of what Bill and his ground-based analogs are doing go a long way to start addressing how do we provide psychological support for crews that are outbound on future missions where Earth is a speck, and when you try to call your family 20 minutes later, they'll say, "Yeah, I didn't understand what you said, Dad." So anyways, we joke about it. That's going to be an important thing, especially when you're on a 1.5 year round trip mission. Part of what we do on Station, in fact, a big part that has evolved quite a bit, is science. So another thing just to keep in mind is while ISS is a test bed, it's a test bed for a lot of things. The Station program headquarters is interested in using Station and all of its capabilities to figure out how to burn down risks to go beyond low Earth orbit. But at the same time, it's our job to make sure we don't compromise the science platform and the science commitments that we currently have ongoing. There's a lot of different things that we do, and again, I'll get back to psych support a little bit. Earth views. Crew members like to spend a lot of time. In fact, we hear this routinely when they come back home. A lot of their free time is spent just gazing out the window, looking at Earth, enjoying a perspective of our planet that nobody else can enjoy. And we also use it as a great platform for seeing different events on the Earth, whether it's the night view, hurricanes, different events like volcanoes. So we do a lot of science actively, and we're doing a lot of Earth observations. Complex operations, we do maintenance, extravehicular activity, spacewalks, a lot of different dynamic vehicles, visiting vehicle traffic, cargo resupply, new crews coming up, taking people home, something that Sam touched on a second ago, which will be an important factor to consider if you go beyond low Earth orbit, is how do you get rid of your trash? Seems like a trivial thing, but practice at home. This is something you can do at home. Keep your trash inside your house. Don't throw it away every week. Keep it in your house for a while. See how you like that. You need a way of disposing of trash. When one of our cargo ships that delivers all kinds of new stuff, fresh fruit, things like that, we also use it as a big trash can to dispose of all kinds of stuff. If that thing gets delayed, it causes problems. So there's a couple of things that make an astronaut unhappy. It's lack of coffee, so you need your cargo ship, and it's not able to get rid of the smelly trash. You need your cargo ship. So the ability to get rid of trash and how we're going to do that when we go outbound beyond low Earth orbit, another thing that needs to be factored in. Where you put your stuff. I searched for some good photos. There's a lot of good photos of of where you put stuff on station. Logistics, stowage, inventory, where things are is an important thing to keep in mind. So let's talk considerations. You've heard a lot of this already. The two aspects of station that I think are relevant for exploration is, first, what are we doing on station as a test bed? I'm going to hit on a couple of examples here in a second. But secondly, it's what we've learned from being involved in space station that either is applicable or we're going to need to change or evolve in order to what, you've heard folks refer to severing the bonds with Earth, or going outbound from Earth and being less dependent on Earth. So themes that have emerged in my just listening in on a couple of days of this conference are autonomy is going to be important. Again, dealing with the crew element or the crew system and how we keep them healthy and happy on their, and trained, well trained, all the way out to Mars and back. Those are themes that emerge that are very important, in addition to all the system design and how you get there and the propulsion and the staging and things like that. So things that we need to work on. Some of these station offers a great opportunity to do investigations of autonomy. You heard Bill Gerstenmaier on Tuesday talk a little bit about we're doing some tests with autonomous procedures. How do we make procedures that we do routinely, because station was designed for the ground to be in charge of running the station and the systems and system management. The crew's in charge of science. We designed it that way intentionally. We send 3,000 to 5,000 commands a day just from Houston to keep the station functioning. The crew does all the science, they fix things when they need to, and they have limited interaction with the systems. I don't think that model will work the same way as we get further and further from Earth. We talked about logistics, the stowage, the communications delay, the emergency response. We train heavily on the ground with our crews. Emergency response. All the ground teams are in sync. We have a single set of procedures that everyone breaks out in case of emergency. The crew does their part, and they go through a certain part of the emergency response, and then they basically can stop, consult with the ground on where do you proceed from here. That whole scenario, depending on what emergency you might run into, could be up to 30 minutes, an hour, and then you're talking to the ground. You're farther away, there's got to be more autonomy built into the total emergency response and recovery from an emergency. How do you maintain crew proficiency and the skills? Somebody in one of the sessions yesterday talked about how do you keep people engaged, not just on the ground, but the crews going outbound. What are you going to give them to keep involved? Maybe it's learning new skills, certainly proficiency. We've learned through station that you can train somebody. We start training 15, 18 months before a crew actually flies, and we learn that they have to maintain their proficiency in some of the fundamental skills like EVA, robotics, how they interface with different payloads. We've learned that some of that is not as effective, and you need to do it with onboard training, and maybe you can cut out some of that pre-flight training and just do it on board. So things like that, learning new skills, that's going to be important when you have a crew that's going to be getting in a lander to go land on the surface of Mars, then go do complex spacewalks or whatever we call Mars walks. They got to refresh those skills. They could be outbound for 4 to 6 months. A lot of their pre-flight training will start to wane. And then, of course, the systems. They got to be simplified. A lot of stuff we have on station. I say station's fairly robust. We have a lot of redundancy. Redundancy equals mass. Spares equal mass. You got to come up with a way to make things easy to maintain, easy to operate, easy to fix. So those are things just to consider. So why station? And we've already touched on most of this. It's just a fancy color chart, so I'll talk for a second anyways. But things that make station an interesting and useful test bed. It is an isolated facility that's currently manned, and it is an operating platform. A lot of the ground analogs don't offer the isolation and the continuously operating platform. You hear about Antarctica. One of the things that is more difficult or challenging to insert some of our studies in Antarctica is it's a currently operating base. So is space station. We have to fold in any of these kind of experiments that we want to do, whether it's involving the crew for their behavioral tests or whatever, or new systems, into an existing scientifically operating laboratory, so it's a little bit more challenging, but that also makes the fidelity of the experiment much greater. The systems are high fidelity. Your test subjects, I don't think it gets any better than the test subjects we have, and you have an experienced ground team in a controlled environment in which to conduct your tests. So I think these things make station an attractive platform for doing tests. So enough of all that. What are we doing? There's several different categories that the station program is trying to keep track of what kinds of things are we doing to prepare for exploration. Technology demos and critical system maturation. Things like robotics. Dr. Fong's going to talk in great detail about robotics and what we're doing in the areas of telerobotics and robotics from the station. Believe it or not, long-duration clothing. Cut down on mass. If you can create clothing that doesn't smell after you wear it for a while, I'd like that here on Earth. But anyways, testing things like that, very important. The fluid physics, and these are things that talk about how you can make more efficient engines, make more efficient use of fuels. The life support systems, obviously a heavily critical thing. We're testing some of that right now and have been for a while on station. This is the 3D printer, believe it or not. We have a 3D printer that got delivered to station. We're going to be doing tests on 3D printer. Hopefully that will cut down on a lot of spares and things you have to fly if you can manufacture what you need when you need it. Communications, the delay-tolerant networks, other advanced high-def communications, laser technology, ways to downlink and communicate high-bandwidth information at relatively low power levels. And then combustion technology, not only for emergency response and understanding how flames behave in zero-gravity environments, but also, again, for development of engines and fuels and understanding combustion in space. Ops simulations and techniques is more in my area. How we communicate, how we make a crew autonomous, taking procedures that we run day in, day out that require interaction with the ground and expect interaction with the ground and make them autonomous. Thinking of, here are all the things you could run into that could trip you up on this procedure, and embedding that in the procedure so that the crew can effectively get through nominal or just normal running of the procedure and handling problems that run along without requiring interaction with the ground. And then minimizing the interaction with the ground to be such of, instead of Houston, we have a problem, Houston, we had a problem, here's what we did about it, and then our teams are focused more on the tactical, strategic of working out how we're going to instruct the crew to respond after they've gone as far as they can. A lot of different things. We look at comm delay testing. We're going to do some tests with the Human Research Program, supporting them actually in a comm delay test to get a start understanding behavioral aspects of if you delay certain activities in which you expect normal back and forth communications, how does that change the dynamic between the crew ground? How does the crew end up having to rely more on themselves as a team as opposed to the ground crew team? So there's a lot of interesting things that we're continuing to do there. Crew planning and self-scheduling as opposed to the ground doing all the nitty-gritty, detailed scheduling, giving the crew a little more autonomy in how they plan things that they need to do or want to do, and replan things if they need to. And then finally, the medical aspect, a huge piece of this. This is one of the primary reasons we're trying to fly the one-year crew, is to get a better handle on what things do we put in place as countermeasures or to keep a crew healthy on station, both physically, psychologically, things like that. Are those measures that we use for 6-month crews adequate for 1 year, and can we extrapolate those to beyond low Earth orbit missions? And finally, where are we heading? Again, you've heard allusion to one-year crew, and hopefully we'll do several of those to get a lot of data points on that. We have been doing stuff, so the message, and I think Dan Dunbacher said yesterday, is, hey, we're already on the path to Mars. I would say, based on what we've been doing with station and the lessons we've learned already and things we have been testing, we are on the path to Mars using station already. So it's not just beginning, it has begun. We're just making it more of an emphasis. There's other missions where the international community is heavily involved, and one of the things we do well on station and have gotten better at is the international involvement. So how we coordinate with international partners, which will be important as we go beyond low Earth orbit, because things cost a lot of money and we don't have it all ourselves. So these are the kind of things that are involved in Station, what Station's doing today, and where I think Station can fit in the grand scheme of things.
Good morning, everybody. I don't think I'm going to talk to you about the Microsoft Office security alert here. Let's see.
Please.
Perhaps we can click the cancel button. While they're fixing that, as Sam said, I run the Intelligent Robotics group at NASA Ames, and one of the key things that I do as part of my job is management of a project called the Human Exploration Telerobotics Project. This is a project that's been going on for 4 years now. It's one of the key things that NASA is doing to try to understand how robotics can really support, enhance, really enable new things with human exploration. NASA, of course, has had a very long and rich program, and we've heard earlier during this meeting about robotic exploration in deep space. One of the key questions for us, though, is how do we enable human exploration in deep space? And one component of that, I would contend, is improved use of remotely operated robots. So today I'm going to talk to you a bit about some of the work we've been doing on Space Station. Last year we did a series of tests that looked at the whole question of how we can have astronauts in orbit control planetary rovers on a surface, be that the moon or heading out towards Mars, be that in orbit inside a human spacecraft, or perhaps on a moon such as Phobos. And I'm really actually very happy to have gone immediately after David, because he set the whole context of ISS as a very nice laboratory, an orbital platform to do a lot of this work. Some of the issues that he talked about in terms of training and proficiency, especially for complex operations. And believe me, if you ever tried to remotely operate a robot, it's a complex operation. Those are the kinds of issues that we really need to address. Those are the kinds of things that we need to understand how to really deal with if we're going to be effective at using humans and robots together. So let me begin by starting. This clicker will work.
Buttons left, right.
I did that. Is the clicker on the right computer?
You got your answer.
There we go. Let me begin by pointing out the Global Exploration Roadmap, which I'm sure many, if not all of you, are familiar with. In fact, I'm sure there's some in this room who contributed directly to this document. The current version from last year has a section on human-robotic partnership. And one part of that is in the area of what in the report is termed telepresence. There are a lot of definitions around the world through different communities what telepresence means. But in this one in particular, it defines telepresence as the teleoperation, so the remote operation of a robotic asset on a planetary surface by a person who is relatively close to that surface. And so to us, what that obviously means is how do you have robots controlled on a planetary surface, for example, on the surface of Mars, from Mars orbit. The thing about this, of course, is that that sounds great. The idea that, hey, you're in a spacecraft, you're inside a shirt-sleeve environment, you're not down on the surface inside a pressure suit. How do you control the robot? Sounds easy, but the reality is we don't really know what's all involved with that. How do you design the system? What are the key drivers for that? What are the issues that are associated with handling problems? How do you interact with the system? What control modes do you use? How do you interact if you're have a need to talk to somebody back on Earth and it takes a long time to get an answer and have support? How do you contrast operations of a robot by perhaps one or at most two operators versus the large-scale teams we have today that are operating the Mars rovers? All these questions are good questions, and there are a lot of assumptions about what's easy and what's hard. So one of the things that we have been doing is starting to take a look at how do we address these questions? How do we really test these hypotheses, examine these assumptions to find out what we know is fact versus what we just hypothesize as maybe a key problem. And I think that if you look at this in sort of a broad scheme, there's clearly a roadmap of doing testing on Earth, in-ground analogs. Unfortunately, one of the other panelists today who was expecting to be here, Pascal Lee, if he had been here, I'm sure he would have talked about the value of doing ground analog testing in places that are very similar to Mars. We've actually done a fair amount of work with Pascal and testing things up in the Canadian Arctic. purely in terms of ground testing. ISS, of course, is a higher fidelity simulation, especially for this kind of work, where you're looking at humans in orbit and robots on the surface. And as you go beyond that, of course, doing operations in cislunar space on the moon is a natural progression to where we, I think, all would eventually like to be at Mars, be that in Mars orbit or on the surface of Mars. So to look at this whole roadmap, we've been conducting a series of tests over the past several years. Last year, we moved on to testing in orbit on the station. And I'm going to spend the rest of this time here just giving you some insight into what we did last year. I should point out also that the NASA is not the only space agency interested in this. Both the Canadian Space Agency and the European Space Agency also have projects that are looking at the overall question of, if you have crew in orbit, how do you operate effectively robots on a surface? But for NASA, our focus last year was a project that we called Surface Telerobotics. The key points here, we're trying to look at how do you test crew control of a semi-autonomous, so not a fully autonomous, but also not a completely joystick robot on a surface. Trying to look at really the interaction between humans and robots. How do you command, how do you control, how do you monitor, how do you supervise those robotic systems? And for us, a key part of this was trying to obtain baseline information. We want quantitative data about the operations, data about communications, data about human performance, data about robot performance, data about the overall system utilization. Those are key quantitative figures that we need in order to engineer future systems. The way we did this was to spend several test sessions last year, about 11 hours of total test time involving 3 different crew members on the space station. The first test in June with Chris Cassidy looked at using robots for doing survey work. The second session with Luca Parmitano was doing deployment of a simulated telescope array. And the third session in August with Karen Nyberg was doing inspection documentation of that deployed structure. So this is just a short video to give you some sense of the kind of work we were doing. So on board station, this was from the second session with Luca Parmitano. He's using a space station computer and a graphical user interface to remotely operate this. This is the K-10 planetary rover outside at one of our test areas at Ames. Here K-10 is driving across the surface. Luca has commanded it to move forward and move into position to deploy a simulated radio telescope. You can see here that the robot is moving purely autonomously. In this case here, it's equipped with a number of sensors, onboard software, to allow him to remotely operate this at different levels of control. The overall test configuration for us was an interesting one. We're trying to use station as a good analog for future deep space missions. And part of that had to do with how do we manage the communications between the operator, the astronaut on the orbiting platform, and the robot on the surface. It's quite a bit different from other payload experiments we see on station. Most of the time on station, we have activities going on board, and we care a lot about getting data from orbit down to the ground. Here is sort of the inverse. We care a lot about the data that comes from the surface, from the robot, from its sensors, from its instruments. How do we send that information back up to the station? It's a very sort of mirror kind of configuration against the typical things you see on station. It's also very asymmetric. Here, because the robot is semi-autonomous, the commanding, the data that goes from orbit down to the surface, relatively low. If you look up here on this chart, about 2 kilobit per second on average. Contrasted with the amount of data, the rich amount of data from the surface gathered by the robot, goes up on the order of about 1 megabit per second. So an interesting configuration from a networking perspective, interesting from the point of view of something that the crew usually doesn't do. They're used to operating robots on the other side of the bulkhead, large positioning arms. This was, I think, really a unique study that we did last year of having them reach out far beyond station, all the way down to the Earth. Here's a picture, a close-up here of Chris Cassidy. This was during our first session here. You can see here that he's working with a space station computer. Now, there are lots of different ways to command robots. Those of you who've been involved with robotics probably aware there are a lot of different modes of control. Very basic joint level control where you're controlling everything at a very low level to much higher levels of control where you're commanding at task level. In this case here, Chris is using this interface here to command the robot in a mixture of modes. One of those has to do with commanding the robot in a supervisory fashion where he's telling the robot to go execute a trajectory, to go, in this case, conduct surface surveys. And as I was mentioning earlier, he was using this robot, the K-10 robot, to do this work. The robot was equipped with a number of different instruments, camera, 3D LiDAR to get 3D data, and it was operating around a mixture of terrain, boulder fields, places with slopes, places that actually had simulated craters. We actually required Chris to spend a fair amount of time doing a variety of tasks, not just driving from point to point, but being able to negotiate obstacles, such as boulder fields. This is a video of the second session, give you a little bit of idea of the kind of interaction with an interface. Luca Parmitano here is watching as the robot's driving. He's getting real-time telemetry, real-time feedback. The display is showing real-time 3D graphics representing obstacles, representing terrain hazards, providing him with camera views. And here, it's an interesting thing for me is that all three of these crew members had no prior exposure to this robot. They had never seen the robot in person. They had never visited the site. And so one of the key questions we're looking at is how do we really effectively train them? How do we do this training, especially because they had never seen the robot on orbit? Really interesting set of questions there about how do you do this in a way that is effective, that allows good training, good skill acquisition, rapid proficiency acquisition. Something that I think that as we look further and further in deep space is really, really critical. I think that one of the key lessons that we learn from this is that it's very important as you design these sort of systems, especially where there's an amount of autonomy on board, that you design it appropriately and that you educate the user in such a way that they can make good use of that. This is just a slide that shows you the kind of activity that Luca was doing. Here behind the K-10 rover is a deployed piece of polymod film. It's representing a simulated radio antenna. And his job during the second test session was to go lay out this array, laying out 3 of these simulated antenna structures. Just to give a little insight too, one of the key things that we were looking at during our testing last year was the interaction between crew on orbit and mission control. Now, of course, as we get out deeper into space, the communication delay gets longer. It's more difficult to have any sort of interactive communication between astronauts and mission control. But one of the key things we're trying to understand is how do you do that effectively? How can the ground still provide support and provide supplementary information to crews when they get further and further away, and trying to have ways for mission control at the same time to have good situation awareness of what's going on to these activities in a way that's very different than we do today in low Earth orbit. During our last session, Karen Nyberg spent quite a bit of time using the system to go inspect and document the array that had been deployed by Luca Parmitano during the second session. Here she's working with the same interface. All 3 crew used the same interface, but in different ways, and moved the robot around to inspect the deployed antenna. Now, I said earlier that a key part of our work was really trying to acquire quantitative information. We set up a wide variety of data collection methods. Some of those were automatic. We looked at the data communication to and from the robot, to and from the user. We looked at the interaction with the interfaces, which modes of control were crew using. We did recording of their activity. We also had interactive questionnaires. We looked at their workload. We looked at their situation awareness level. All of this is a massive amount of data. This is probably, I think, about 15 gigabytes of logged information from these 3 test sessions. And if you're curious about this, there's a paper that we presented in just a few weeks at the ISS conference in Montreal. Happy to talk to you afterwards if you want more details about some of the results. I want to wrap up with one final thought, though, of this set of tests we did last year is really only the starting point. We basically created a single point system. We did a series of studies of different tasks. But that's really only the beginning. There are a lot of other things that I think are needed if we want to actually understand how can we enable human crews to make use of planetary rovers at a great distance, especially if you're looking at the control of rovers on, say, the surface of Mars from orbit. One part of that is trying to understand really the integration aspects. As you look at using deep space human spacecraft, are there things you can do to really enable a more effective system? If you're taking a spacecraft, for example, into proximity to Mars and you have rovers on Mars, well, one thing you might be able to do is to offload some of the computing that typically today has to be done with rad-hard processors on the surface and take those functions, put them into the spacecraft, make use of the spacecraft's facilities, resources, and onboard services to do some of the work that today we can only do on a very impoverished computer on board the surface. A second area is really trying to look at some of the different tasks that are going to be important. The work that we did last year was really fundamentally structured tasks. They're not that dissimilar for some of the work that's done on orbit. We defined crew procedures, activities that had a very well-defined start to finish. A lot of the work that we see on Mars today, a lot of the work being done by the Mars rovers, they're typically more unstructured because there's more discovery involved. I think a key part of future work that needs to be done is really trying to understand, especially if you have crew involved with this, of how do they really handle these very unstructured tasks, these tasks that you cannot adequately, fully train, fully prepare for ahead of time. And then the last area, something that we just really, I think, scratched the surface on during our testing, was looking at the whole interaction between multiple humans and one or more robots. The question of how does ground control interact with the system? How do we look at high latency versus low latency interactions? The Mars rovers today are very high latency systems. This kind of system where you have humans in proximity, low latency. And the question is, how do you blend the two together and still end up with a system that is very efficient, very effective, and ultimately allows you to accomplish what you need to do on the surface of another planet. I think I'll end there, and I pass it back to Sam.
All right, thank you. Do we have any questions?
Perhaps you covered this, but I presume the robots and the space station are in continuous contact, even when the station's on the other side of the planet?
So during our tests, of course, we're making use of the station, and our requirements for the testing were, we wanted, quote, as much continuous coverage as possible. That wasn't always the case. We did have periods of loss of signal, but during those periods of loss of signal, we did not continue to operate it. We only operated when we did have continuous coverage.
Okay, but in principle, you could bounce the signal off ComSat,
Sure.
and you could do the same on Mars. And
Sure.
do you have an idea of what sort of assets now would be required in the ComSat constellation to support what you're doing? And how do you extend those assets to support an astronaut managing 5 or 10 rovers to do a task? Any concept of how that's coming along? Or?
Well, I think yesterday during one of the panels, Lisa May was talking about the communication infrastructure around Mars and how that's critically important for robotic exploration today. I firmly believe that robotic exploration in the future, especially if you're looking at humans operating one, or as you were alluding to, multiple robots, is going to require that communication infrastructure. But one of the things that we then need to understand is, well, what are the requirements? What's the amount of bandwidth? What latency can we tolerate?
Right.
What availability and coverage do we need? I think part of that can be addressed by the different modes of control to the extent the robots are more autonomous and you don't need to have a high-def video signal, continuous coverage. That will reduce some of the requirements. But it's very much tied, I think, to your ability to operate those systems in some effective manner.
Also path redundancy, so
Yep.
you use more than one coupler
Yep,
at a
exactly
time.
right.
Do you have?
Let's try to get into another question, please.
This is a follow-up question for that to Dr. Fong. Looking at the image of the guy who was driving the rover on the ground, one of the screens showed a detailed map of the area where he was going. So I would assume you're going to need very high-resolution mapping of the areas where you're going to be running the rovers?
Well, I think that today, if you look at the way we do operations on Mars, for example, we do take advantage of the orbital assets to get high-resolution imagery and then to create high-resolution 3D terrain models. That certainly is very helpful if we have that information. In our testing last summer, we also, in real time, constructed 3D maps based on the sensor information that came back from the rovers. And the combination of data from orbit and from the surface, I think, is really important because obviously you can't rely just on one source of data.
You don't want to drive into a hole.
Well, exactly.
Another question?
Yeah, I assume that before you had astronauts spending their time doing this stuff, you had people on the ground. And what I would be what you're expecting to learn from having astronauts do it at the ISS is comparison with the baseline of people operating on the ground. So what's the answer? Is it much harder for folks in space to do that as it is for people on the ground? Because once we get on the surface of Mars, most of the robotic operation is going to be by folks who are in the base or habitat. They're already on the ground, so that would be a better analogy. So.
Well, so two quick answers to that, and I don't want to monopolize the panel, and we have other fine people here too. One part is that yes, we have been doing quite a bit of testing with users, different operators on the ground. A lot of the analog work in the past involved with projects like Desert Rats and the Human Mars project that Pascal Lee runs, have looked at the question of having ground operators remotely operate systems. Part of that is because you can use robots to do lead scouting, short distance ahead. But it is true that we did take information from those kind of tests, and the information we gained last year is meant to be at least one data point in comparison. I think longer term, part of the real challenge, however, is trying to understand what are the right metrics to use to assess the productivity of a system. It's really difficult to place a single metric on the productivity, the quality of scientific return. And you're trying to figure out, well, hey, are you just interested in improving the ability for you to collect data, or are you trying to look at the ability for you to make discovery? And the second one is really hard to put a figure on.
Bill?
Sorry, guys, but I'm going to ask Terry a question as well.
Oh, come on.
I'm Bill Mackey. I'm with the Canadian Space Agency here in Washington, and grew up on the International Space Station, the robotics world. And Terry, thank you for explaining the fact that Canada is also interested in telerobotics. And in fact, Bob Thirsk, while he was an expedition crew member on station, he did a similar telerobotic experiment with an arm inside the lab at the Canadian Space Agency. We didn't drive a rover, but he did drive an arm telerobotically from space station. So my question has to do with autonomy. Well, the architecture, you talked about architectures, and clearly if we're going to go to a cislunar station, or we're going to have a station that's going to orbit around the moon and drive robots telerobotically, that's one thing. But you mentioned the fact that there's going to be a trade between telerobotics and automation. So the autonomous aspects of robots on the surface of the Mars, doing what it is, assembling stuff, navigating, looking, drilling for water, assessing what's in the water, not necessarily the efficiency of the science or the exploration or the discoveries you're going to make, but the efficiency of the robotics techniques itself. What at Ames are you guys doing to make robotics smarter?
So, I'm glad you asked that question from a couple perspectives. One is I did talk with Bob a bit before we ran our set of experiments last year to get his impressions. And it's always, I think, important for us to, as engineers, as researchers, to try to get the feedback from, astronauts who are actually in space, who have had that experience, to understand what their concerns are, the things that they feel are important for their activities. At Ames in particular, the name of my group, coincidentally, is the Intelligent Robotics Group. I sometimes think maybe we should call ourselves the Stupid Robotics Group, because our robots are not intelligent as humans. We are looking at autonomy, I think, in one important area, and that is we're really trying to improve the low-level robustness and resiliency of these systems. So, for example, the robots that we work on, the planetary rovers, are very competent in their ability to drive from point to point. They can look at obstacles, they can figure out how to get around an obstacle. They're not smart enough to make decisions and really decide where they should go to look for a particular sample or identify a target. But they are smart in the sense that they can drive very competently. And I think that kind of autonomy, the ability for us to offload the low-level control that today we typically have to do in a real rate-controlled joystick manner, that is a really empowering, productive thing to do, to improve the autonomy of the system at that level, so that humans don't have to be continuously in the loop doing manual control.
So
I like
to add to that,
Bill?
Sam, though, then why is telerobotics important? If you can make a smart robot to go from A to B, then why can't it drive around the rocks or over or avoid holes and such?
Yeah, well, so our robots do that, and during their testing last summer, they did that, but we need the humans involved to make the higher level decision making. And at that point, I'm going to stop talking and turn it back to Sam.
I got one quick question, and then that I'll need to ask Bill why I got you here, and then we'll end the panel. After we do the one-year crew rotation, do you think it's worthwhile for the ISS partners to repeat Mars 500?
It's actually a good question. The main reason for going the whole 500 days on Earth is the psychosocial, the behavioral, and performance. And it seems like we can probably learn enough from one-year missions in environments like that that we don't have to go for a whole 3 years. So the things we've been proposing is to go to 1 year, and we're planning another one of those in about 2018 if things go right. And whether we need additional ones after we learn what we learned from the station to try and get more details on what we observe will be still TBD.
All right. Well, that's it for us today. Let's thank the panel.